Hi there. So today I'd like to do an example RL circuit problem for you. If you haven't already watched the previous lecture going through the theory of RL circuits, then you should definitely do that before you watch this lecture, which works one of the example problems and uses the equations that we cover in that lecture. So the problem that I'm going to do for you today is from Knight's textbook, Knight's Calculus-Based Physics textbook, Chapter 34, Problem 79. So it asks a question about this circuit shown here in the figure at the lower left corner, where you have a 30-volt battery and then a switch, followed by a 10-ohm resistor, and then parallel paths here, two parallel paths. And in one path you have a 20-ohm resistor, and in the other path you have a 10 millihenry inductor. So the question says, the switch in the figure has been open for a long time. It's closed at t is equal to 0. What's the current through the 20 ohm resistor, part A, immediately after the switch is closed, B, after the switch has been closed for a long time, and C, immediately after the switch is reopened? So, first of all, there's a way to do this that involves very little math, and it's kind of what I call the conceptual version of what's going on with this RL circuit. So we'll go through that first, but then I do want to grind through the solution to the math so that you can see how to do a problem if it's not quite so open and shut as this one is, so to speak. Pardon my pun. Okay, here we go. So the way that the question is phrased is all important here. It's asking for what's happened immediately after switches are closed, after switches have been closed for a long time, and then immediately after switches have been reopened. Okay? So when it says it that way, what it's saying is that you're having the largest and strongest reaction from the inductor, and then no reaction from the inductor. And it's because of how dIdt works. See, when you've got this circuit here, you've got a battery here, it says the switch has been open for a long time. That means that there's no current flowing anywhere in the circuit. And then when you close that switch, the rate of change of the current, dIdt, is going to be largest right there at the beginning. Remember that the equation for the back EMF of an inductor is proportional to dIdt. So that means that the back EMF that the inductor can generate will be largest right when the switch is closed, okay? Now, if the back EMF is largest right when the switch is closed, then that means, you can assume, basically no current is flowing through that inductor. So it acts like an open switch, at least for a split second, okay? Now, what that'll mean is that all of the current of the circuit will flow from the 30-volt battery through the 10-ohm resistor, the 20-ohm resistor, and back to ground. Now remember, when you have resistors in series, the resistances add. So that means that you have an effective 30-ohm resistor hooked up to a 30-volt battery. And that means that through that 20-ohm resistor, you're going to have 1 amp of current. According to Ohm's law, delta V is equal to IR. Okay? So right when the switch is closed, the answer to part A is that right when the switch is closed, you're going to have 1 amp of current. Now, the next one says, what happens after the switch has been closed for a very long time? The answer to that is that after the switch has been closed for a very long time, you have a steady state current. There's no time rate of change of the current. It's reached its equilibrium value, okay? So if there's no dIdt, then there's no back EMF. And that means, since we're assuming a perfect, beautiful, perfect circuit with no resistance in the wires here, which of course isn't true, but since we are assuming that for this problem, then that means that there's going to be no resistance in the parallel branch that has the inductor in it. Well, if there's no resistance, then this acts like a short, okay? It acts like a short around the 20-ohm resistor, and so it bypasses that 20-ohm resistor, and everything goes through that inductor. So the answer is, if the switch has been closed for a long time, then there's not going to be any current flowing through that 20-ohm resistor because the inductor will act like a short. Now, how much current would be going through the inductor? It doesn't really ask this directly, but you do have to figure it out in order to do part C. So how much current would be going through that inductor after the switch has been closed a long time? Well, the inductor acts like a short with no resistance. the 20 ohm resistor is bypassed. So basically what you've got is a 30 volt battery in series with a 10 ohm resistor. Now, according to Ohm's law, delta V is equal to IR. That means that you'll have 3 amps of current going through that inductor. Okay, now like I said, the problem didn't ask that, but it did ask in part C what would happen immediately after you reopen that switch again. Okay, well, if you open the switch, then that cuts the battery off from the circuit. Okay, the battery's cut off. That means that you just have an inductor in series with a resistor, and current makes this little loop over here on the right-hand side of the circuit. The inductor is going to try to maintain. That's what inductors do. So that means that since it was 3 amps when the switch was opened, it'll try, at least for a split second, to stay 3 amps. Okay? So immediately after the switch is reopened, it'll be 3 amps. So that's the conceptual answer to the problem. And you have to do very little math in order to get that. What you would have to do math for is to figure out what was going on with the current at any time t, okay, in any of the branches. So if it asks you for some very specific time, like 0.0005 seconds, then you'd have to solve for what the current is in the general equation and then plug in for that time. So let's assume that it did ask that so that we can figure out how to do that on harder problems and go for it. All right. So what you have to do to solve this problem is use Kirchhoff's laws. So, sorry, my throat's a little scratchy today. So what's going on is that you have this 30 volt battery, and I've drawn in all of these Kirchhoff's law problems, what you want to do is you want to label first, step number 1, label the currents, show their directions and all that kind of stuff. So that's what I've done here in step number 1. I've got current I flowing through my 30 volt battery, and it would go through that 10 ohm resistor, and then at this junction right here, it would split off into 2 parallel paths, okay? So I'm going to label the current that goes downward through the 20 ohm resistor as I1, and I'm going to label the current that goes through the 10 millihenry inductor as I2, okay? And then, of course, I1 and I2 would join back up at the junction at the bottom of the circuit and then route back through the 30 volt battery, so you'd have I flowing back into the 30 volt battery. So my currents are labeled, my directions picked. Now remember, if you draw the wrong direction, all that happens when you end up solving the problem is that you get a minus sign in one of your currents. So it's no big deal. Don't be afraid to make a wrong choice. Okay, step number 2. You're going to write down your loop rules and your junction rules for the circuit, the Kirchhoff's laws. So here we go. I like to do my junction rule first. And so the junction rule here is that the sum of the currents into the junction equals the sum of the currents out of the junction. So going into this junction here up top, I have current I, so that's on the left-hand side. And then on the right-hand side, I have I1 and I2 flowing out of the junction. So I have I is equal to I1 plus I2. And that's my junction rule. It would be a junction rule 2 for the bottom, but it's the same junction rule, so it doesn't matter. Okay, now I've got to pick loops. The deal is that I need the same number of equations as I have unknowns. Now, I've already identified my unknowns here. In this particular problem, my unknowns are my currents, and there's 3 of them. So I need the same number of equations as unknowns. I've got 1 equation already from my junction rule, so I need 2 loop rule equations in order to have the same number of equations as unknowns. So here we go. The first loop that I chose is the one that goes from the 30 volt battery up through the 30 volt battery to the right through the 10 ohm resistor, down through the 20 ohm resistor, and then back to the battery. So that loop rule is going to be plus 30 volts minus 10 ohms times I minus 20 ohms times I1 is equal to 0. Now let me explain. I'm going what I call the right way through the battery, which is from the ground to the positive terminal, so that voltage is added. And then if I'm going in the same direction that I've labeled the currents, right? So I labeled the current as going to the right through the 10 ohm resistor and down through the 20 ohm resistor, and that's the direction I'm walking around my loop. So that means that I subtract off the voltage for those resistors. And of course, that's Ohm's law, IR, okay? So that explains my first loop rule equation. Now my second loop rule, the loop I've chosen, is the battery up through the battery, across to the right through the 10 ohm resistor, down through the 10 millihenry inductor, and then back to the battery. So that's the second loop that I've chosen for my loop rule. So going through that, I've got plus 30 volts minus 10 ohms times I minus 10 millihenries times di2 dt equals 0. Okay? So the 30 volts, yet again, I'm going the right way across the battery, and then in the same direction as the current flow. So that means that the voltage for the resistor, the 10 ohm resistor, subtracts off. Delta V is equal to IR. And then remember that the equation for the back EMF is minus L times di dt, where L is the self-inductance and di dt would be the rate of change of the current. In this case, the 10 millihenry inductor is seeing current I2, so it's minus 10 millihenries di2 dt. Okay? So that's my loop rules. Now, the next step that I always do is to, I usually label my main current as I, and then the split-offs as numbered currents. So what I usually do, and this is entirely up to you, but what I usually do is I solve for my numbered currents in terms of my main current, and then plug that back into my junction rule. Okay, so that's kind of what I've done here. I've solved for I1, which is the current through the 20 ohm resistor, using my loop rule equation that contains I1. So that's I1 is equal to 30 volts minus 10 ohms times I divided by 20 ohms. Just pretty simple algebra right there. Okay. Now I'm going to take that and I'm going to plug it back into my junction rule so that I'll have I just in terms of I2. Okay. So here I have I is equal to, plugging back into my junction rule, I2 plus I1, where I1 is 30 volts minus 10 ohms times I divided by 20 ohms. So when I simplify, that gives me the equation of I2 plus 1.5 amps minus 0.5 times I. Okay? Now I'm going to plug that back into my second loop rule equation that involves the inductor. Okay? I'm going to plug that back in. But first I want to rearrange it just a little bit and make it a little simpler to plug back in. So dealing with that equation, I'm going to take the 0.5I that's on the right-hand side and add it to both sides, and then I end up with 1.5I is equal to I2 plus 1.5 amps. And I would end up with I is equal to 2/3 I2 plus 1 amp. So that's the simplification of my new junction rule there. Okay? Now I'm going to go back to my second loop rule equation, which was the 30 volts minus 10 ohms times I minus 10 millihenries times di2 dt is equal to 0. Okay? This is an equation. It's a differential equation. Ideally, to solve it, I would just want I2 and T as my variables, right? I2 and T. And then I could get an equation for the current I2 with respect to time. But to do that, I have to eliminate the current I. So that's what I've got right here. I've got the equation linking from my junction rule, I and I2. So I'm going to plug in for I into this differential equation. So when I do that, I get 30 volts minus 10 ohms times 2/3 I2 plus 1 amp minus 10 millihenries di2 dt is equal to 0. Now I've achieved my goal. In a way, I've got I2 and T as my variables there. So I have a differential equation that will be easier to solve. So my next steps just involve the simplification of that equation and getting it ready to do the solution, which I'm going to do via integration since it's just a first-order differential equation. So here I have, keeping with the algebra, 30 volts minus 20/3 ohms times I2 minus 10 volts minus 10 millihenries di2 dt is equal to 0. You say that 5 times fast. Okay, so I combine my volts, and I get 20 volts minus 20/3 ohms I2 is equal to 10 millihenries di2 dt. You can see I put my di2 dt term on the right-hand side. Then what I would want to do is I would want to put everything with time on one side of the equation, everything with I2 on the other side of the equation. So to do that, I multiply both sides by dt over 10 millihenries so that I've got my di2 isolated on the right-hand side. And then I'm going to divide out by the 20 volts minus 20/3 ohms times I2. Okay? Then on the left-hand side now, I have dt over 10 millihenries equals di2 over 20 volts minus 20/3 ohms times I2. Okay, so that's my differential equation now. And all I have to do is integrate both sides. So when I integrate my left-hand side, it's a pretty simple solution. I'm just integrating dt. The 10 millihenries is a constant. And if you think about it, what's happening here is I'm closing the switch at t is equal to 0. So I want to solve for some random time t, right? So I have a general equation. So I'm going to integrate from 0 to t. Now, that integration dictates what the limits of integration are going to be on the right-hand side. Remember that there's no current flowing at time t is equal to 0 because the switch has been open for a long time, okay? So that means that the current is initially 0, and I just want an equation for I2. I don't know what it is, okay? So I'm going to integrate on my right-hand side from 0 to I2. Okay, so that's what I've got there. Now I have a differential equation with a solution here. I'm integrating, okay, solving it. In order to do this integration, a simple substitution is in order. Now, the way that I like to do my substitutions, I'm sorry, math teachers, it's a little lazy, but what I do is I do the substitution, I don't change the limits of integration, and then when I've done my integration, I plug my substitution back in with the old limits. I know, it's a little lazy, but it's easier, and I like to do it that way, and it works. So here we go. My substitution is, I want to make this so that I'm just integrating 1 over a variable. So I'm going to call this whole denominator y, some random choice. So here I have y is equal to 20 minus 20/3 ohms times I2. Okay, 20 volts minus 20/3 ohms times I2. Then the dy would be minus 20/3 ohms times di2. Okay, so that means that di2 would be minus 3/20 inverse ohms times dy. So I plug that in for di2. And then plugging in for y, I end up with minus 3/20 inverse ohms times the integral of dy over y. All right, so when I integrate that, I just get natural log of y. So I have minus 3/20 times the natural log of y. And when I plug back in for what y is, that gives me minus 3/20 times the natural log of 20 minus 20/3 ohms times I2. And then I evaluate those in the limits from 0 to I2. Whew, blah. Okay. Now, when you subtract natural logs, what you can say is that you're dividing the arguments of those natural logs. Remember that generically, natural log of A minus natural log of B is the natural log of A over B. So you can look those rules up if you've forgotten them. But I'm going to use that rule to evaluate my limits. So here on the next slide, what I have is, first of all, I got rid of the 3/20, the negative 3/20, by multiplying through on both sides by minus 20 over 3. So here on my left-hand side, I have minus 20/3 ohms times T divided by 10 millihenries. Okay. And then on the right-hand side, in evaluating my limits, which were 0 to I2, I end up with the natural log of 20 volts minus 20/3 ohms times I2 divided by 20 volts. Okay? All right. Now, I don't like to leave things in terms of natural logs. Very few people do. They're just not great in terms of visualization. So what we like to do instead is to get rid of that, and to do that, we'll raise it to the power, of course, e to the power. So if I do that to both sides, I'm going to get e to the stuff, e to the negative stuff on the left-hand side, and then the e will cancel out the natural log on the right-hand side, and I'll have 20 volts minus 20/3 ohms times I2 divided by 20 volts. Now, what I've done here on this line is I've gone through and multiplied by my denominator, which is 20 volts. So on the left-hand side, I have 20 volts times e to the minus 20/3 ohms divided by 10 millihenries times t. And that equals to, on the right-hand side, 20 volts minus 20/3 ohms times I2. Now, I really want a nice solution where I have I2 equals stuff, okay? So to do that, I'm going to add this 20/3 ohms times I2 to both sides, and then I'm going to subtract this exponent. And then I'll multiply through times this stuff multiplying I2. When I do all that, okay, I get 20 volts times 1 minus e to the minus 20/3 ohms divided by 10 millihenries times t, okay, divided by 20/3 ohms. Simplifying, I get I2 is equal to 3 amps times 1 minus e to the minus 20/3 ohms t divided by 10 millihenries. Okay, now I'm getting really tired of saying 20/3 ohms, I'll tell you that. So I'm going to put things in terms of the time constant from here on out. Remember that the time constant tau for an RL circuit is equal to the inductance L divided by the resistance R. So here, that would be equal to 10 millihenries divided by, one last time, 20/3 ohms. So that ends up being 0.0015 seconds, or 1.5 milliseconds. So that's the time constant of our circuit. Now, we've solved for the current through the inductor. Once we have the current through the inductor, we can figure out all of the other currents using the equations that we've already derived. So I of t, for example, I, the main current that comes from the battery, is 2/3 I2 plus 1 amp. So since we've solved for I2, which is the current through the inductor, we also know I. And if we know I, we also know I1, because there's a simple relationship we derived that relates I1 and I. It's 1.5 amps minus 0.5 times I. So that means that I can solve at any time t for all of the currents. So I did that here in Excel and I plotted them, okay? The current through the inductor is the blue line. That's I2, okay? And you can see that it starts out at t is equal to 0 and it approaches 3 amps, which is what we knew the solution to be. I've gone through about 3 time constants or so on this plot. If I extended it out further, then I could have a better approach to 3 that would be a little easier to see, but you can see that it's getting there, okay? All right, now the current from the battery is the orange line, okay? And so it starts out, as we predicted, at 1 amp and goes up towards 3. And the current through the 20 ohm resistor, you can see, starts off at 1 amp, which we predicted, and decays towards 0, okay? So that all agrees with the conceptual predictions that we made without doing any of this hard math. But after doing the hard math, I can solve for the current at any time t, and I don't just have to look at the extrema. Okay, well, I hope you enjoyed that, and if you have any questions, let me know, and I'll see you around.